So we are in week 3 of the course. Um, Today we are going to look at um, um, the, the CDF of random variables, probability density functions, some examples uh, before we look at some problems. So this would be kind of the agenda for today. So so last week we saw what we meant by a random variable. We defined random variables. Uh, let's say we started off with the probability space. Uh, we defined a random variable to be a measurable map from uh, capital omega to R. Now, we also saw last week that a random variable x uh, did not be left continuous. It always has to be right continuous, but it does not have to be left continuous. And a quick proof of that is as follows. So, so what do we mean by left continuous? So we say that any function f uh, is continuous at a point x if it is continuous from the left and continuous from the right. That means that if you have a sequence xn, um, if you have a sequence xn plus which converges to x from the right, uh, which is denoted in this way. So that means you have x over here and you have a sequence xn plus which converges to the right, converges from the right. It's denoted in this way. And if you have uh, another sequence, let's say xn minus, which converges from the left, which is denoted often in this way, which means that you have some sequence xn minus uh, tends to x in this way. So then we say that a function f, in this case, our function is uh, yeah, we say that a function f is uh, is is continuous if both if it is both right continuous and left continuous. Means that limit uh, limit n tending to infinity f of xn plus is equal to f of x. This is right continuous, and limit n tending to infinity f xn minus is equal to fx. This is for left continuous. Now, of course, the function that we're interested in over here is uh, is our CDF function, which we will denote as uh, f subscript x, and the CDF function is always right continuous, but it's not necessarily left continuous all the time. So why is it right continuous? Well, um, well, if we write something like f of x of xn plus, where xn is some sequence which is converging to x from the right, then by definition, this is equal to the probability of x belonging to, or yeah, x belonging to minus infinity comma xn. Right. So now the sequence of, so because xn plus uh, tends to x. Um, uh, so this set x belonging to minus infinity comma xn plus this set also converges. Sorry, this set converges to this set. Okay, and we discussed last time that if we have a descending sequence of sets, uh, in other words, uh, just think about it in this way. Let's say this was x. Here, let's say you have some xn, and this is all the way up to minus infinity. And so we have this sequence of sets, which is first this, and then maybe this, maybe this, and then you have this descending sequence of sets. And you saw that if you have such a descending sequence of sets, uh, then they will converge in probability. This is a property of all probability spaces. It follows from the fact that uh, uh, that probability of a countable union, uh, the countable disjoint union of sets, is the sum of the probability. So that limiting property of probability is from where we get this result that limit n tending to infinity probability of x belonging to minus infinity comma xn plus is equal to probability of x belonging to minus infinity comma. Right. So this is just restating uh, right continuity. But what about left continuity? For left continuity, um, now I assume that you have a sequence xn minus, which is converging from the left to x. Now here's the catch. So if you consider the sequence of sets, which is x belonging to minus infinity, comma xn minus, sorry, then now this is an ascending sequence of sets because as xn grows, as xn is increasing towards x. So as xn grows, you have an increasing sequence of sets. But the limit of this increasing sequence of sets is is actually, so let me write it on this way, limit n tending to infinity, uh, x belonging to minus infinity, comma xn is not is actually equal to x belonging to minus infinity, comma x, and this is open on the right. Now this is different. Now this is by definition this is different from this, and there lies the catch. So um, now if you take now again the limit of probabilities would exist. So limit n tending to infinity, uh, probability of x belonging to minus infinity, comma xn, which is just uh, limit n tending to infinity fx of xn minus. This is equal to probability of x belonging to minus infinity, comma x open. And now this is uh, this need not be equal to f of x of okay. So the difference between this set and this set is just in this point at this point x. Okay. So uh, so in order that continuity must hold at x, we require that probability of x belonging to minus infinity comma x and sorry x is equal to probability of x belonging to minus infinity comma x closed. Okay, and this would hold precisely if uh, if probability of x equal to x is equal to 0. In other words, a random variable is continuous at a particular point x if it assigns 0 uh, probability to that point mass. In other words, if you have a continuous random variable, then the probability of a particular point, just a specific point, is equal to 0. So a continuous random variable always assigns 0 probability to point masses. Okay, and and therefore a corollary of this is as follows: is that if you have a um, sorry, if a is equal to an is a discrete set, or when it not be a discrete set, can just be a countable set. Well, that's just equivalent, by the way. Uh, if there is a countable set of points, then the probability of x belonging to uh, a is equal to 0. Okay, if x is a continuous random variable. Right. So hopefully it's clear when a particular random variable is going to be a continuous random variable. Okay. If you have any questions, you can always stop and ask me.
Measurable properties of CDF.
Yeah. Measurable properties of CD. What do you mean by measurable properties of CDF? I
Whether
didn't quite get.
whether the CDF is a measurable function, whether it
Oh.
is differentiable at all points. Some
Okay, okay. Let us discuss that. Measurable functions of measurable properties of CDF. Okay, so the CDF, well, what it is, the CDF, if you have X, which is a random variable, um, then the CDF is a map from R to R. Um, so precisely, it's a map um, from R to 0, comma 1. Now, okay. So now, um, so now let us ask if
Good
f
evening,
of x
sir.
is a yes,
Good evening, sir.
yes, good evening.
Is the CDF FX differentiable almost everywhere for any random variable?
No, 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 no. Just take a simple example, right? Um, just take an example. Just take a discrete random variable. So, what happens if you have a discrete random variable? So, for a discrete random variable, what does the CDF function look like? The CDF function, uh, well, you asking if fx is differentiable almost everywhere. Um, well, no. F of x need not be differentiable almost everywhere. Um, but if you ask me a counter example,
Yes, sir. It is
I'll have,
good enough to show a counter example for this.
uh, um, let me think about it a little bit. um,
Excuse me.
yeah,
If x is a continuous random variable,
yeah,
right,
yes.
then the CDF of that continuous random variable is a smooth function. So at each one of the points, it has a definite tangent. Therefore, it is differentiable at each and every point. If
Oh,
x is a
if x is a continuous random variable, okay, let me write down the
Yes,
statement.
sir. For any random variable. For
no,
any
No, just
random.
let us
no.
go one.
Let's write down the statement that he's saying. Uh, lemma if x is a continuous random variable, then can you can you uh, can you say the statement? Um, then
F
then f
f
of
sub
x is smooth, is differentiable.
is a smooth. The graph of f sub x is smooth, and f sub x is differentiable.
Hmm. Okay.
If x is a discrete random variable,
Hmm.
they
No, no,
have
no. Let us first resolve this statement. If x is
okay
a continuous random variable, then f of
mm,
x is differentiable. Is this correct?
everywhere.
Everywhere. Okay. So let us think. Uh, um, let us take a random variable that looks like whose CDF function looks like this. Okay. Um, mm, yeah. Okay. Um, Something like this, and then maybe this part is like okay. What is of course it's not going to be differentiable at a point like this, right?
Mm.
I mean, we can always have a CDF function that looks like this.
How many points can you find? Is it countable number of points at which they are
Yeah,
not?
that's a good question. Is the so this is a non-trivial theorem, but I'll have to check on this. The the CDF function can have wait 1 second. Mm, Just give me a second. Mm, no, I don't think you have this requirement where it has to be differentiable uh, at uh, at a countable number of points. Uh, I don't think there is any such requirement. But I mean, to come up with a counter example, right now I'm not able to give you a counter example. Just give me a second. Let me think a little bit. Just give me a moment. Yeah. Yeah. I mean, there are certain distributions, and these distributions are highly non-canonical distributions. So there is a distribution called the Cantor distribution. Um, Again, I'm looking this up. It's not something I came up with. Um, so the Cantor distribution is defined on the Cantor set. Okay. So the Cantor set is defined in this way. Um, it's defined in this way. it's a it's a it's a descending sequence of sets. It's defined in this way. So let's say you start off with some interval. Let's say 0, 1. Just give me a second. So let's say you start off with the set 0, 1. Okay. You call this set C0, right? So C1, what you do is that you remove the middle 1/3 portion of the set. So from 1/3 to 2/3, you remove that part of the set. So this is like 0, 1/3 uh, to 2/3, 1. Okay, so this is C1. Now, now C2. So C1 looks like this. Okay. Now C2 is again you remove uh, the the middle one-third portion of the two intervals. Okay. So in general, in this way, Cn is obtained from Cn minus 1 by uh, removing the middle third of uh, the intervals in uh, Cn minus 1. Okay, so this is how Cn is obtained. And the Cantor set is defined as the limit of this procedure. Okay, so C is equal to intersection of Cn. Okay, now of course, this is a highly non-canonical set, and this set is an uncountable set. Okay, it is known that the Cantor set is an uncountable set. Um, Now there is something called this. Just give me a moment. Uh, hmm, okay. Hmm, hmm, hmm. Right. Okay. Right. So the Cantor random so there's this Cantor distribution, which is there's a very nice description of that distribution. It's defined in this way. So what are you doing with the Cantor set? So we have 0, comma 1, and we are uh, yeah, and we are basically um, right. So essentially, what we are doing is that we are chopping it up into three parts, right? And uh, you're removing the second part. Okay, so these parts are included. Right. So the way the Cantor random variable is defined is that you perform a sequence of so you take a sequence of Bernoulli random variables which are independent and identically distributed, uh, and uh, so this you can sort of think in this way. So you define these BNs, which are 0, comma 1, IID Bernoulli random variables. Okay, and you define this X to be equal to sum over of um, 2/3 of Bn. Yeah, n equals to 1 to infinity. Okay, so you can think of it in basically this way that uh, that uh, so you know like like uh, uh, like a base, right? Every number you can express as a base 3 number, like just like you can express a number in base 10 or in base 2, which are binary digits. You can also express every number in base 3. Now, if you uh, express a number in base 3, so then what happens is that, let's say you have you write a number like 0 comma 0 point some number, let's say a, okay, where a belongs to 0 1 2, right? So now what happens is that, let's say um, let's say you consider all numbers which lie in C1. Okay, so C1 is basically this set. So all numbers which lie in C1 can be defined as the range of this random variable 2 by 3 B1. Okay. Well, not exactly. That's not exactly true. But what is happening is that, so 2 by 3 B1, what I said is not exactly Uh, true. So 2 by 3 B1 is equal to 0 when B1 is 0, and it's equal to 2/3 when B1 is 1. Okay. So in other words, if you look at the set C1, which is third and 2/3 to 1, it's either this value or this value. Okay. Now, of course, uh, when you consider 2/3 of B1 plus B2, uh, uh, okay, I made a mistake. It's actually 2 by 3 to the power n. Yeah. So when you do this, when you consider 2 by 3 of B1 plus B2 by 3. Okay, so that is like the second decimal place. Okay, and likewise, if you have, so all essentially all numbers in the Cantor set uh, can be uh, can be expressed in this way, right? And so this, yeah, so x is a random variable that takes values in the Cantor set, and yeah. So now the thing is that at each point of the of the Cantor set, x is not differentiable. Let me just write it down. At each point in the range of x, uh, f of x is not differentiable. Okay, it is, however, a continuous random variable. Okay, so yeah, so this statement is not true. Of course, fx is not differentiable everywhere. It is not only not differentiable everywhere, it is also not differentiable almost everywhere. So you can have an uncountable set. Well, I mean, if you write, is it is it not differentiable almost everywhere? Okay, so when we say almost everywhere, what we mean is that it is not differentiable on a set which has zero measure with respect to the Lebesgue measure on R. Now, at least in this counter example, which is this Cantor distribution, the Cantor set itself has is a set of measures zero. So uh, well yes. So in this case, it does satisfy the property that x is not differentiable in a set of measures zero. But to say whether x is if x is can x can the CDF be non-differentiable at um, a set which has non uh, uh, which has a measure of non-zero. So that would be equivalent to saying that there exists an interval such that inside that interval f of x is not differentiable at all points in the interval. So let me just write it down. What it means is that um, there exists an interval uh, from alpha 1 comma alpha 2 such that uh, at each x in alpha 1 comma alpha 2 f of x is this f of x is non-differentiable. So this is basically the condition. This is basically the condition for saying that a random variable x can be non-differentiable. Basically, the CDF can be non-differentiable at at a set of non-zero Lebesgue measure. Right. This is this is the equivalent condition for that. And um, I think this is not true. Uh, I don't think there can exist an interval where f of x uh, is discontinuous. Sorry, is non-differentiable at uh, um. Let me just think a little bit. Um, I don't really know the answer to this. Uh, I think this statement is not true. Uh, in other words, um, the CDF um can be a CDF is differentiable almost everywhere. Um, just give me a second. Um,
Sir, in case of discrete random variable, it is not
hmm.
differentiable. I think for a step function, there are much jumps in the curve, or in there is not smooth curve. That's why I think that's why it is not differentiable. Maybe
Okay.
for
Uh,
in for discrete
no,
case.
what you're saying is not true. Um, okay. Just give me a second.
For
Let me just
discrete case, we always get a
no.
step
For
function.
discrete case, it is no. For discrete case, it is differentiable. It is differentiable almost everywhere. Just give me a second. Write down a theorem, which is uh, Hmm. Mm, yeah, let me just write it down. Let me draw a theorem. It's a theorem from real analysis. Um, if f is a uh, if f is a uh, non-decreasing function with bounded variation, then it is differentiable almost everywhere. Yeah. So this is the theorem, and uh, CDF is basically a theorem that satisfies this, um, because the CDF is a non-decreasing function. It has bounded variations, and therefore it is differentiable almost everywhere. Um, so yes, the answer to your question is the answer to what you're asking is yes. Now, what happens for you are asking something about discrete random variables, right? Well, for discrete random variables also they are differentiable almost everywhere, right? So, what is a discrete random variable? A discrete random variable takes values in a discrete set. Okay, so discrete random variable. So x, so the range of x is basically some discrete set. Uh, is a uh, discrete set. Okay. So if we have a discrete set like that, then what does then what does the derivative look like? Well, the derivative is not defined. Let's let it out in this way. The the derivative of f of x does not exist at possibly the points of D. But D is a discrete set, right? A discrete set has measure zero. So if you plot the CDF of a discrete random variable, it will look like a step function. It will look like this basically.
Yes, sir. It's a step
It will look
function.
like it's a step function, right? But a step function does have derivative defined, right? The derivative is not defined only at these steps. Only at this point the derivative is not defined. But here the derivative exists, right? Here the derivative is equal to zero. So it is. So you understand by what is meant by almost everywhere, right? Do you understand what is meant by almost everywhere? So he said this is a phraseology that occurs uh, ubiquitously in measure theory, where we say that a property holds almost everywhere. If we say that some property P holds almost everywhere, then what this means is that uh, the set of points or the subset of points where the property P fails to hold is a set of measures zero. This is what it means. So here the property P is being differentiable, and the points where the property P fails to hold is a discrete set. Discrete sets measure zero. Okay. So when I say measure, I mean the Lebesgue measure on R. Okay. Um, hopefully it's clear. Like uh, you need to know a little bit of measure theory to kind of understand this statement. Um, right. Okay.
Yes, sir. Where the function is discontinuous, the derivative is undefined. Okay.
Yes, yes, of course.
Yes, sir. Ah, yeah. Thank you.
Yes, yes. But it should be clear to you that for every random variable, the CDF is going to be differentiable almost everywhere. Okay. So hopefully it's clear to you. So what you were asking is true, and the discrete random variable is not a counterexample. Okay, it is not a counterexample. Okay. Oh, okay. So this is not true, of course. Mm, okay, just give me a second. I'll be back in 1 minute. Uh, okay. Um, right. So I think Mr. Muthukumar was asking me one question, which is that is x if x is a random variable, is the CDF a measurable function? Yeah. So let us look at that. Um, so fx is a map from R to R, and actually not from R to R. It will take values in 0, 1. Okay. Right. So if we now ask the question, is f of x measurable? So if fx is measurable, then that is equivalent to asking, is uh, is fx inverse of um, 0, comma a uh, measurable? Is this a measurable subset of R? Okay, and of course, yes, this is a measurable subset of R. Um, Yeah, to yeah, I mean, uh, well, it suffices uh, to ask this question, which is easier to answer. Is this a measurable subset of R? And And yes, the answer is yes, this is a measurable subset of R. Well, you kind of answer it in this way. So fx, well, what is fx? Fx is a non-decreasing function. So if you have this non-decreasing function, and if you ask what is fx inverse of 0 comma a, so then you you do fx inverse of a. So that what you can do is you can do fx inverse of a. Okay. Now there are two possibilities. One is that uh, one is that uh, f of x is continuous at a, or f of x is not continuous uh, is not continuous at a. Okay. Now, if f of x is continuous at a, then of course what you need to do is the this fx inverse of this. So basically, this set fx inverse of 0 comma a is going to be equal to um, uh, minus infinity comma uh, the uh, the limb soup of this set, or not limb soup, uh, the soup of this set. Right. Um, hmm, yes. And if fx is not continuous at a, uh, then fx inverse of 0 comma a is this. So we stated before that f of x is differentiable almost everywhere. Well, it follows that f of x must be continuous almost everywhere, right? So because it is continuous almost everywhere, so there is a result. Again, this is a result from measure theory, that a subset which is continuous almost everywhere must be a dense subset of R. Okay. Uh, Right. So because it's a dense subset of R, you can always find a sequence AN. Sorry, no, not AN actually. Um, you can always find the sequence. Uh, right. So okay. So let's say f of x is discontinuous at A. So if it is discontinuous at actually I write A, but A is not the right. Um, Actually, this is not the right term to use. What I mean is basically as follows. So if there are two possibilities. One is f of x inverse of a exists. Okay, this exists and is not a null set. And the other possibility is that f of x inverse of a does not exist. Uh, Right. In other words, it basically skips a value, right? Like, for example, if you have a step function like this, let's say you have this, and then you have this. Okay. So yeah, if you have a step function like this, then of course, um, you can have a value which is skipped. Uh, okay, so in this case, what you do is that um, you take the um, yeah, you take the smallest or you take the uh, largest uh, a prime less than a, such that uh, fx inverse of a prime exists. In other words, what you do is that um, you take this set. You consider this set infimum of not yeah, I mean infimum of, not infimum actually, supremum of a prime less than a, such that a prime is in the image of fx. Right. And this you can always do because I mean, this will always exist because the graph of f of x, I mean, uh, the graph of f of x is going to be, um, uh, is also going to be uh, yeah, it's going to consist of a set of intervals, right? The graph of f of x will always consist of a set of intervals. So let me write it down in this way. The graph of f of x fx will consist of a set of intervals. Okay. So then what you do is that, let's say you take this a prime, let's call this like some a minus or something like that. You take this a minus, and then fx inverse of 0 comma a is going to be equal to um, fx inverse of 0 comma a minus. Yeah, hopefully it's clear. Um, okay.
Sir, I have another question.
Yes,
How can we express CDF as a piecewise function?
as a piecewise continuous function, what you mean?
Yes, sir, as a piecewise function.
No, I mean, when we say piecewise, it's always piecewise followed by something. Piecewise
Yeah,
continuous.
piecewise
Piecewise,
continuous.
yeah, yeah, yeah. Yeah, I mean, yeah. So the CDF can have discontinuities at almost at most a at most a countable number of points. Uh, yes, the CDF can have uh, discontinuities at most a countable number. And yeah, so what you do is that uh, so whatever the points where the discontinuities exist, you kind of uh, remove that. You consider those intervals. Okay, so there uh, will always exist intervals. Okay, um, so there will always exist this set of intervals. I It has these intervals, so on, um, where the uh, right hand side of the interval is where the rightmost point of in is uh, less than equal to the leftmost point of in plus 1. Okay. So you'll always find some intervals in R that look like this, uh, where the function is going to be continuous. And then you define it in piecewise continuous in that manner. So let's say the simplest case that you're dealing with a discrete random variable. Then what you do is that uh, um, so let's take an example. X is a discrete random variable.
Excuse me, you completed the proof that f of x is capital Fx is measurable.
Yeah, yeah, yeah.
So if we consider capital Fx as a function from R to R with Borel
Mhm.
measure, still it is
Yes,
measurable.
still it is measurable. Yeah, because because what is happening is that uh, you will anyway have to consider sets of this kind, right? And let's say this A is not in 0, comma 1, but if this A is outside 0, comma 1, then
Yes.
yeah, so yeah, that's a good question. So if you take fx inverse of let's say uh, some uh, minus infinity to minus 1, let's say. Okay, so then it is a null set. Yes. If you take something like fx inverse of 0, then of course this is equal to minus infinity. Okay. Now when we consider the Borel measure, in the Borel measure, minus infinity and plus infinity are not considered to be a part of Borel measure, right? So of course fx inverse of 0, um, well, fx inverse of 0 um, may not be defined because you have minus infinity. So one way to kind of circumvent this problem is to do it in this way. So there's something called an extended measure on R. So in this extended measure, is written down in this way. It's called R bar, where this is R, and you have adjoined minus infinity and infinity to it. Okay. So oftentimes what we do is that this is called the extended real line. So oftentimes we consider fx as a map uh, on this extended real line to from instead of r. So for basically from r bar to infinity, or from r bar to r. then all of these sort of uh, these uh, um, these this pathologies kind of go away, and we can say that uh, uh, that affects the CDF is actually a measurable function.
Only
Yeah, I
if
mean
it is
generally don't.
only if it is an
Hmm?
extended real line, right?
Yeah, if it is an extended real line, then definitely. If it is not an extended real line, then fx inverse of if you do something like fx inverse of one, let's say, then the fx inverse of one, well, um, it's still a measurable set, right? I don't see why it should not be a measurable set. Um, yeah, it is still going to be a measurable set.
Okay.
There's no reason why it's not still measurable. Yeah, yeah, but generally we consider the extended real line for a lot of these when we're considering this, uh, just so that we can also include infinity uh, into it. But otherwise, also it's still measurable. Okay. All right. Um, yeah, I guess that was we had a good discussion today. I mean, some of these things, even they are not really, even I don't, they're not really at the tip of my fingers. So yeah, this is a good discussion today. Um, all right. So now, yeah. Yeah. So now we have seen the CDF. Now, of course, uh, we want to ask if the CDF can actually be differentiated. Um, in other words, um, if I have the CDF, uh, which is fx, does there exist a function small fx such that um, fx of any a is equal to integral 0 to infinity fx uh, then uh, d mu of x. Okay. Okay. Now, what is this d mu of x?
Sir,
So,
I think it is integral over 0 to x, I think.
oh, sorry. Yeah, yeah. What? Sorry, I'm writing it completely wrong. Yeah, integral of minus infinity to a. Sorry, thanks.
Thank you, sir.
Minus infinity to a fx d mu of x. Okay. Now, what is this d mu of x? So, so the so uh, so on R you have the standard Lebesgue measure. Okay. So typically, when we write an integral like this, like think of some other function g, which is a measurable function, and you write something like g dx. This dx is the Lebesgue measure on R. Okay. Okay. Sorry. Not f of x. This is f of x dx. Right. Um, now, Now, if you have a random variable x from omega to r, uh, let us say explicitly omega and mu is the measure defined on omega to r, then you have basically you can push forward this measure mu to a measure on r. So mu, let me write it in quotes, mu can be pushed forward to a measure on r. So this push forward measure is written in this way. You can sort of write it as uh, mu x, and mu x of minus infinity comma a uh, is equal to mu of x belonging to uh, minus infinity comma. Okay, so in other words, so x is a function. So you can invert x inverse of, so you do x inverse of minus infinity comma a. That gives you some measurable subset in omega, and you take the measure of that. Okay, so so what happens is that the random variable x is a way to push this measure on omega to a measure on r, right? So so this measure is precisely what we call the distribution on r, right? And this distribution you often write it as this um, as this um, as this CDF function. So now, of course, we are asking this question that uh, is mu x, um, or rather, can I write? Can I? Can we say that for any measurable set A in R, A measurable, there exists a density f, small f of x, such that um, such that mu x of A is equal to integral of fx um, dx. But this dx is the Lebesgue measure on R. And the integral is over this measurable set A. Um, okay. Uh, so if such a if such an fx exists, then fx is called the density function of the random variable s. Okay. Um, just give me a second. I'll be back in 1 minute.
Jumi madam, Jumi.
sorry. Yeah. Yeah. So when such a when such a density f of x exists, we say that fx is absolutely continuous. Uh, continuous, and the measure um, mu x is um, is uh, is absolutely continuous with respect to the Lebesgue measure on R. So the Lebesgue measure on R, I'm going to just write as m of R. This is the Lebesgue measure on R. Yeah, so oftentimes we denote it in this way, and well, so the criterion for such a density function to exist is basically as follows. Um, if it basically is as follows: condition for density function to exist is that if A is any subset of R such that the measure of A is equal to 0, this is the Lebesgue measure on R. If A is 0, then mu x of A is also equal to 0. In other words, uh, in other words, uh, if A is a set of measures 0, then x takes values in that set A with a probability of 0. Okay, uh, that is x takes values in A with a probability 0. Now, yeah, essentially, if you understand Radon derivative, then the density function on of the random variable x is just the Radon derivative of this measure. So this f is sometimes symbolically represented as in this way. It is written as uh, d mu x upon dm of r. This is the Radon derivative. And of course, the condition for this Radon derivative to exist uh, is that uh, mu x has to be absolutely continuous with respect to the Lebesgue measure on R. Um, yeah, there are some equivalent conditions to say when the density function will exist, but they're somewhat non-trivial. I mean, in my opinion, I don't see one condition as being particularly uh, useful over another condition when it comes to computable purposes. Um, but yes, I mean, so one thing to keep in mind is that uh, uh, the density, uh, a density function will not exist if you have random variables which assigns a non-negative mass to a point. So in other words, discrete random variables cannot have a density, right? Um, yes. So yes, discrete random variables note uh, if if x takes uh, values in any discrete set with uh, non-zero probability, then x, then a density that is this PDF of x will not exist. Okay. Um, yeah, that's right. Uh, now when such a PDF exists, the PDF is going to be equal to the derivative of the CDF. So the PDF is equal to the derivative of the CDF. Okay. Yeah, I mean that kind of brings us to the end of the material for this week. Um, the next week, um, the next week we can have two possibilities. Um, One is that instead of doing like a theoretical discussion session like today, we can have like a full 2 hour problem solving session that kind of covers week 1 to week 3. I can look at some problems. I can give some problems
Okay.
uh, from some other textbook, and we can have like a collective problem solving session. Uh, does that does that sound good?
Okay. Thank you.
Yeah. Otherwise, I
Finally,
guess. Yeah.
finally,
Please.
so I want to ask that assignment 3, problem number 1.
Okay. Okay.
It looks all options are correct. Please kindly check that one.
Hmm.
Assignment 3, problem number 1. All about
Oh,
measurable. If the problem is okay, it's all right. It looks
okay.
all
Let
5
let me check.
options are. Huh?
Okay. Let me check. Just give me a second. I'm opening the problem. This one, right? That's right. Yeah.
Uh,
Um, yeah. All of the options seem correct to me. Um, hmm. Hmm. Okay. Yeah. Um. Yeah. Yeah. Okay. I'll think about this problem. I think all the options are correct, but I will have to think about this problem a little bit. Uh,
that if and only if part is also correct, you know.
yeah. 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 It is correct. The fourth option is definitely correct. 100%. Uh, it has to be between options. I mean, if the problem indeed has like a solution, then it will be like either the third or the fifth one. But I don't think they were wrong. I think they're correct only. Um,
Fifth one is correct because it is differentiable almost everywhere.
yeah, yeah, yeah.
Whether it is discrete or continuous, it is differentiable almost everywhere.
Yes, yes, yes. That's right. Uh, yeah.
Third, CDF is a measurable function.
Hmm. Yeah, that may I may need to think about it a little bit. Is it a measurable function? Um,
Maybe they think R to 0 comma 1 instead of R to R, or maybe
hmm, uh, that should not be an issue though, because
hmm,
um,
you explained that also.
yes, yes. I mean, even if it is still R, it still doesn't cause any. Problem. Um,
Hello.
yes, yes. Uh, yeah. I mean, all the options seem correct to me. Give me a second. Let me check quickly. Yeah, 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 I mean, all the options are correct. Uh, I don't know what. Yeah, all options are correct.
Okay.
Yeah.
So we'll meet next Friday.
Yes.
Thank you.
Thanks. Thanks.